Ciao, here is a conversation with Nathan Kutz. Professor Kutz teaches at the University of Washington, Seattle, and is one of the leaders of the Artificial Intelligence Institute in Dynamical Systems, founded by the National Science Foundation. Together with colleagues and collaborators, he is my superhero in the field, not necessarily because of the interesting way in which he put together AI and dynamical systems, and not necessarily because of the great results he got in the years applying these ideas to dynamical systems, but I would say mainly because of his passion. Is really, you can feel it, and because of his methodology. So you can really see the transparency of his thought process and therefore of his goals. And this is transferred into the fact that his papers are freely available online, his data as well, and his codes as well. You can use them to do your research, do your works, run your simulations and your experiments. This could be it about the conversation, but it's not. We actually talked about some technical things like the relation between the Kopman theory and the inverse scattering transform in the context of partial differential equations. We talked about this tension between having interpretable models and powerful black box ones. So you can think of dynamic mode decomposition, kernel methods, sparse identification of nonlinear dynamics, and things like this on the one hand. On the other, autoencoders, neural networks, and things like this. So this is it. There are a lot of things we discussed as well. I hope you enjoyed the episode. If you like it, put a thumbs up, subscribe to the YouTube channel, connect with me on Twitter, LinkedIn, and then please, if you can, support me on Patreon. The link's in the description. And here's the conversation. Yeah, so thank you for joining this conversation. I would like to start this episode talking about the way which the University of Washington is going to lead, or is already leading, I guess, the AI Institute in Dynamical Systems. What's the scope of this institute? Who is involved, and what's also its position with respect to the overarching perspective of the National Science Foundation?
Yeah, thanks for asking the question. So that the National Science Foundation has made a commitment to invest heavily in AI, machine learning. We kind of all understand that the world is changing rapidly with with the capabilities we have, with the data, with computational engines that we now have, just our ability to do extraction and processing of data sets that are so large. I mean, ultimately, the unsung hero here that we never talk about is sensors. Mm-hmm. Really, all of this is coming from sensor technologies, in my view, right? What we can do, like you just have to look at biology and see that the rapid increase in, it's remarkable what they can do. Same thing with, however, geophysics, what they can monitor, space satellite imaging, but also these sensor arrays they can place everywhere. So really it's the sensor technologies across all disciplines that have created this massive data pipeline that we need to process and across diverse disciplines. So this is where these AI Institute efforts are coming in from National Science Foundation, right? Is we can't do these by hand or at small scale on laptops. What we need to do is sort of do these at scale to really push forward science. So the AI Institute in Dynamic Systems was one of the funded institutes. It's a $20 million commitment over 5 years. Its particular goal is, to some extent, is to think about classic engineering systems. We're thinking about control theory. We're thinking about how do I build models where AI agents sit on top of them to help decision-making processes, typically in these engineered systems. So things from autonomy to the digital twin, this is sort of in some sense the wheelhouse of this AI Institute, because we ultimately want to build great physics and engineering models. And ultimately what a lot of engineering really wants to do is once you have these really great models, you'd like to control the system and make it do what you want it to do. And do this just from the data that you're acquiring in real time from those systems. So that's really what the focal point is. And what we have is we've built this partnership with the a really fantastic group of institutions that are in the Pacific Northwest broadly.
Mm-hmm.
So, University of Washington is the center point, but we have partners at Montana State University, Boise State University, Portland State University, University of Nevada, Reno, along with Alaska and Hawaii. So that's
Mm-hmm.
kind of our Pacific Northwest hub. And we also partner with Harvard and Columbia to sort of form a team all dedicated towards these efforts around taking these engineering and physics-based systems and understanding them, and also thinking about how to control them and build great models for them from
Mm-hmm.
the data.
And this grant has already started, right? Last year.
Yes, we are now. It started officially October 1st in 2021. It's been an interesting start, obviously due to COVID.
Mm-hmm.
We were going to have a kickoff meeting in October, but we've postponed that, and it's going to be March 16th and 17th. It will be a hybrid format, so we'll have. So actually, since it's a broadcast, for anybody interested, we're going to, people can register from anywhere in the world, and we're going to broadcast all the talks and put all the materials online afterwards. So people can get a very good idea of what we do
Mm-hmm.
and the kind of perspectives we have, and we have an amazing group of speakers, both from industry and academics, to really sort of start thinking about where do we want to be in machine learning and AI in the engineering sciences as we develop this forward. So that's going to be our kickoff meeting, which was going to be in the fall, but now Omicron's starting to come down. It looks like we can have this in person here at the University of Washington, or at least in a hybrid format. And so that's exciting for us to get together finally in person. We've obviously been getting together on Zoom, but that's it's just not as good.
Yeah, not the same,
So,
definitely. Yeah. And how does it feel? I mean, both personally, but also in the sense of work. Like, I mean, I've seen your trajectory, and this was coming, I would say, because a lot of great works. But I mean, is this about keeping being what you've always been, or I mean, has this jump changed the focus, the priorities in the work you're doing?
I think one of the things that this has done is that I think a lot of the people that we've brought together on the team, all of us had a lot of methods around to contribute in this space. But one of the things that the Institute allows us to do is to sort of really build partnerships that can take us further, right?
Mm-hmm.
I think one of the things that I'm really excited about in our sort of modern era of science and engineering is I think there's more and more realization of how much we need partnerships. It is so difficult for an individual to be good at everything. There's just too much to know. And what you really need to do is find great partnerships where you can advance a field together, because your skill set, while complementary, has some orthogonality to it, and it allows people to push further than they have before. And I think that's actually what I'm very excited about the Institute. So a lot of the things that are core ideas of what I have been doing, and also what I've been doing in partnership with Steve Brunton, who is my just a fantastic collaborator and friend. And also, we have this amazing group of jointly advised students and postdocs, but sort of a lot of our focal area on physics informed machine learning, we can now couple with people who can bring additions to this, whether it be in control, whether it be in application areas. So we're excited about what it can do for us in terms of extending our methods, but also these people coming in and extending us and giving us new thought life around what we can do. So I think overall, the hope is that you get this very harmonious working relationship that leverages everybody's skills towards taking this to the next level. And the only other thing I would say with this is that another key piece of the Institute is that we are really committed to making all of these resources, the data sets, the codes, YouTube video lectures are all available, right? So that the hope is that, a grad student across the world can say, I'd really like to get into this area. And there's always been such a big barrier to entry to get into fields. But here you could just say, hey, I've actually have the code in hand. I have the data in hand. I have lectures that kind of really walk me through the state of the art. It just means that people can get started in that research effort and making contributions much more quickly. And I think part of what we want to do with the Institute is allow that to happen and set the stage and an example for others to sort of do this so that we can all progress further scientifically much more quickly.
Yeah, definitely. Yeah, you brought up a couple of points I'd like to go into. I would say that the most interesting is probably how do you see, this revolution in education. So in my perspective, or even in research, I mean, in my perspective, the work you're doing on YouTube, on GitHub, whatever, on the archive, you're really making it hard to people and founders to pretend they're not reinventing the wheel, if you know what I mean. And this is, in some sense, it's automating institutions out of the way. And so I see a negative impact in the sense that, I mean, we always say automation is going to be bad for low-level works, but it feels like it could be, I mean, it may be that we need less universities in the world. I don't know. But yeah, how do you see things forward in this perspective?
Yeah, I suppose I don't take too much of a cynical view of it. I feel like we will definitely change our operating procedures, but boy, I am so happy that PyTorch and TensorFlow are available, so I can do the science I want. So there's a lot of that was engineered and automated, and there was a group of people who did that. But on the other hand, it's put what it means is my start point for some of these problems is much more advanced because I don't have to write all these algorithms myself, for instance. It is an interesting thing, but even automation, we've seen this before, even in the Industrial Revolution, there was these fears. I mean, clearly the world will change, but I also feel that there will be new opportunities. And of course, whenever there's change in the world, it's a little bit unpleasant, right? Because it means that people have to change, or a certain way of doing things is changing. But I think that's just a natural process that to some extent is unavoidable. And I think what we're going to be doing with this is we are going to change the world, and what it looks like for us in the future will be different. But on the other hand, I still think there's a lot of really great places. There'll still be jobs. There'll still be interesting things. I don't think we're going to automate everything out, so there's nothing to do. I think it'll just change where we are in the future. And also, we always have to do the cost benefit analysis and say, well, what do we gain by it? There's some really interesting areas for us here. For instance, obviously, having self-driving cars might be a really interesting paradigm for us, right? Already we have, places like Uber and Lyft who are driving us around, but you could imagine a fleet of automated cars. Does that mean we're going to, so people who maybe drive those cars currently, there'll be other jobs that need to be found, but there we are. But somehow society has always found those things. But if we can have improved safety and that would be a good thing. And personalized medicine, for instance, right? That could be an amazing advancement for us. So I think there's a lot of benefits. There'll clearly be negatives, but it's really hard to project what they will look like down the road. I just know that there's no avoiding progress. It's going to come whether we like it or not. So I think the best thing for us to do is to figure out good ways to do it. Another piece of this for the AI Institute is that we are taking very seriously the AI ethics training for the participants. So I think that's also something good to be aware of, like what are the appropriate uses of data, and how should we be doing things in that space, right? Because I think that maybe that hasn't been given the most thought, because we can just make products, and obviously there's a lot of pressure on Google and Facebook and these companies, Twitter, just in terms of what is their responsibility level and what is their ethics. For us doing sort of more engineering applications and designs, and we're not taking social media feeds and using that data for things. But on the other hand, we will certainly have our own ethical concerns that we have to start thinking about, which, gets us a little bit to this issue. What you asked is, when you project forward the future of AI, what are the negatives that could be there? And of course, there are many that could be there, and we can mitigate some of them by starting to think a little bit ahead of time about how could these things be used in ways that are not good. And so let's start thinking about it now, so we can create a workforce that starts to respect those healthy boundaries.
Yep. Yeah, and so I guess from here we can already start. You already started, but we can go into the applications of these ideas. And particularly for my audience, I saw you published last year a paper specifically on aerospace engineering. So yeah, maybe an overview. You mentioned medicine. I saw you did works in neuroscience. So if you could give us an outline of the application.
Oh, you bet. Yeah, so I will talk about the aerospace. Steve Brunton and I, myself, as well as Krithika Manohar, who was also one of our collaborators. She was a former grad student, and then she went to Caltech for a postdoc and is back now as a faculty member. We've had this long standing collaboration with Boeing Aerospace Corporation. And one of the really interesting aspects of what's going on with them is this idea of bringing new skills to their workforce, right? So a lot of the engineers, if they've been out of college for more than 5, 6, 7 years, maybe even 4 years, and been working there, right? You see the transition that's happened at the university, where everybody's now starting to understand, I need a little bit of machine learning skill. And really all that means is I need to work with data. How do I work with data in intelligent ways to build models, or to help me build my model? And if you graduated more than 4 or 5 years ago, you don't necessarily have that skill set, but it's very clear to Boeing, not just Boeing, but to most industries, that somewhere in the aerospace design process, machine learning has to play a key role, just like scientific computing does, and just like materials testing. So there's this aspects of actually building components, there's designing them on a computational engine, but there's also how do you get the most out of your data and be able to put it into the overall workflow, so that what you're actually doing is creating a better industry, a more efficient industry, because you've actually learned how to use your data to help you design airplanes, to design materials. All of that needs to come into play. And so part of what we were doing with this aerospace, this future of aerospace engineering paper, was really starting to outline what are some of the considerations that need to be made in the aerospace industry. And really what they want at the end of the day is the digital twin, right? This is idea that you could have an entire factory floor, which has all the physics, between physics modeling, but also even management of robots on the factory floor, that you have this virtual world in which, first of all, nobody gets hurt. Second, you can sort of automate this process to see how are we doing, how can we improve, how do we optimize? And so, streamlining the processes on these billion-dollar endeavors, many billions of dollars endeavors like airplane manufacturing, right? If you save 1%, it's a lot of money, right? So this is the kind of thing that I think is a good use of data can really help these companies achieve, right? And so the aerospace industry is close to us because we're here. Boeing has an advanced research center on the campus of the University of Washington, and we've been working with them. But I think every industry is going to go through this, that they're going to figure out that, like, okay, we're an engineering design company, and traditionally what we've done is we have our models, we simulate, and we build. And I think the last piece that you have to add there right now is say, and we do machine learning. We do, when we take our data, how do we build better models and better simulations, or improve the speed of these by integrating now machine learning AI architectures into it. And also, how do you start thinking about, well, maybe our product could be one that we can actually put in intelligent controls into this thing, better than we've had in the past, just because we have better algorithms now.
Yeah, it's definitely this is definitely a place to dig a bit deeper and go into the core, the fun. I would say, maybe correct me if I'm wrong, but optimal control is a big part of your work. And so what are the ways in which you're dealing with this, particularly in the context of data-driven dynamical systems, so for systems that don't have explicit differential equations governing, symbolic expressions governing them, but also how maybe it's more powerful for those problems in which you actually have an equation. I
think of the control problem as fantastic, right? Because ultimately, for a lot of engineering systems, you like to put controllers on them, and you see this, by the way, in the curriculum of engineering. So one of the things that happened at some point, whether it was the 60s or 70s or 50s, every engineering program, electrical engineering and mechanical and aerospace, they all developed 4 or 5 courses on control because they realized how important this was, and they felt like every engineer has to fundamentally know about control theory. And so the Institute has this focus on dynamic systems, but really it's contextualized in terms of engineering systems, which are going to come down to thinking about control. What's, I think, very exciting is that you have so many emerging paradigms around control, data-driven control. So we have, optimal control. You have methods of model predictive control. So you have the MPC frameworks. You have reinforcement learning frameworks. You have things like dynamic mode decomposition with control. So let's say there's these different algorithms, all who have their appropriate uses. So for instance, reinforcement learning, which is something that's being heavily pushed just straight up from the ML side or AI side of things, fantastic architecture if you have enough data to really build. Learning often requires the most amount of data of all the methods that we have. On the other hand, dynamic mode decomposition with control, it's like, I have very little data. I need a model right now. That's the one you're going to go to because it's a simple regression to a linear model that kind of gives you a state estimation for the future, which you might still be able to make some kind of control decisions based upon. So in general, I think at the Institute level, we think about control as, what is the appropriate controller? Well, the appropriate controller, you first have to tell me, like how much data do you have? What kind of, how quickly you're trying to control it? Do you have the ability to do extensive experiments on your system so that you can collect the data you might need for like a reinforcement learning agent? Or are you in a situation where, you're collecting just a little bit of data and you've got to, and the system is such that you're never going to be able to collect massive amounts and you're really always having to extrapolate, then you might want to use a very different paradigm. So I think for us, what we I think want to do is develop an entire suite of potential algorithms and start to think about, well, use the one that's appropriate for the application in hand, right? Or even use them in combination. You may have a system where at least initially you don't have very much data. And so maybe at that, you start off with something like dynamic mode decomposition with control, which is a very fast algorithm needing very limited data. But then as your system progresses and you keep collecting more and more and more and more data, maybe you start changing your architecture because now you've collected enough data to the point where, well, I've been collecting data for a very long time and I actually can now build a reinforcement learning agent, right? I have enough data to be able to really do that kind of problem where I can say, I can calculate these longer term planning trajectories and delayed rewards. But now I have enough data to actually build those architectures that are there, right? Because that's typically very data hungry. Even like, you think about reinforcement learning for like the game of Go, right? That was quite an achievement. But if you just look at the cost of the data that you had to generate to train that model, right? It was it played so many games, right? And there's a lot of engineering systems that playing a game is equivalent to running that system over some kind of trajectory, and you just can't do it realistically, right? So these are all the trade-offs we have to start thinking about a little bit. But it is exciting, and I'm also excited to see what we come up with in the next 5 years, how we integrate strategies, because there might be some really interesting hybrid techniques where we use one model to, maybe I can't generate all the real data, but I use one of my cheap models to generate proxy data for the RL. I mean, there's all kinds of very interesting paradigms that might come about. People are very clever, right? And we're seeing this all the time. People are coming up with really interesting architectures to do better with noise, do better with less data, to be more robust, take care of outliers. I mean, it's really fantastic to watch what people are doing across the community, because there's a lot of really smart people out there doing really great things.
Yeah, indeed. Maybe even more technical, let's say. We gave the menu, we have reinforcement learning, DMD, we have something in between. If we go even deeper, let's say, talking about maybe a bit of the math, but I feel there's this trade-off in AI between neural networks and something a bit more coming out of the theory, maybe less powerful, but more rigorous. Something like that. So I have this tension between, I don't know, kernel principal component analysis versus autoencoders. SIMD, so sparse identification of linear dynamics, and neural differential equations. Do we need both?
Oh, that's a good question. So it's a good question. To some extent, when you try these things on certain models, or let's say toy models, that we see how these things work, right? So let's go to the SIMD versus neural ODEs, for instance. To some extent, you could step back and philosophically you could make arguments of why you'd want to use one versus the other. Like, if you come more from a physics modeling perspective, you might like the SIMD architecture, because what it actually is giving you is like what you grew up with, governing equations, right? So this is your classical education. You took a bunch of courses and you learned a bunch of physics. And what I mean by learning physics, you learned a bunch of different governing equations. Here's what they look like in quantum mechanics. Here's what they look like in electrodynamics. Here's what they look like in thermodynamics, right? So we learn governing equations as sort of, in some sense, these representations of physics, these small, little models that sort of mean so much to us, frankly, right? They tell us about how waves propagate, how heat diffuses, and how they're universal. These same building blocks of governing equations show up in every single application area we've ever seen. So there's a familiarity with it, and there's an interpretability for us that we feel very comfortable with. Now, the computer scientists might push back a little bit and say, hey, well, we need to move beyond that and allow the computer, because, even our visualizations, we're so constrained down to 3 dimensions. And, the computer says, like, look, I can build you models in 10 dimensions. That's still not even that high dimensional. But like for us, like, how do I visualize 10 dimensions? It's right. We can't do it easily. And some would argue that why don't you just let the computer take over at that point, build the models where it needs. Neural ODEs is very nice because it's sort of a hybrid. It's not just here's a neural network that just black boxes. It's really setting up a structure about dynamical flows, right? And so at least in that sense, it's very appealing still to us. And in fact, I'll tell you, we're kind of working on some integration of neural ODEs with SIMD right now. So we're trying to bridge these together. But I think both representations can be very powerful. Where I don't want to overcommit is to say any method is better than any other, because when to me, the gold standard of what we really need to go after, where I'm hoping these techniques can take us, is to multi-scale physics problems. I actually feel that that is where we really need to be going, where a lot of these methods, if we're going to challenge them and break them or have them actually pull things out for us, it's going to be in multi-scale physics problems. We're great about, like, I just mentioned, we go take classes and we do all of our, here's the governing equations in these different areas. But the fact of the matter is the most challenging problems we face today are multi-scale in nature. So there's some fine scale dynamics. You might even be able to write down explicitly what the equations are. But then when you coarse grain them at scale, there's a different physics up here. And the question is, how are these different length scales interacting? Actually, length and time scales, fast scale physics, slow scale physics. One thing that I don't think we're very good at all is multi-scale physics. We're really good at uniscale physics, but the mathematical architectures around multi-scale physics is very difficult. I don't think we've done a very good job there. I think it's obviously a very difficult problem, but my hope is this is really where neurology, Cindy, everything we can bring to the table, autoencoders, coordinate transformations, separation of timescales. How do we train neural networks that can understand it and parse it, and then also understand how they're supposed to fit together? Right? That's where I'm actually hopeful that we finally have some really heavy duty mathematical techniques that could potentially help us take steps in the direction to understanding the multi-scale physics problems. I think, for instance, this is why I think biology is so hard. If you just look at neuroscience, we're trying to understand the brain now, but fundamentally the biggest challenge there, in my view, is it's so multi-scale in space and time. And you're trying to understand like your behavior out of this. So let's call that's the most coarse-grained level, the macro level of space and time, right? My decision process after I've taken in all this brain activity and I make a decision to make choice A versus choice B, but it all started at these exceptionally fast timescales of neural firing rates, right? You're down on the milliseconds and microsecond level, but then it generates things that are happening for me, decision levels of minutes, right? How do you parse that? And just simply brute force calculation of computation of like, well, I'll just resolve all scales. I don't think that's going to work for us. Well, we've seen that when we do that for a lot of our multi-scale systems, we end up with a big HPC framework where the solution I get out really doesn't match a trajectory I wanted. Like, it's not like it matches anyway. So I really would like to understand how they connect. And that's kind of what we're, I think, really wanting to get after.
Right. And then when you talk about multi-scale physics, you mentioned the brain, fluid dynamics, so turbulence.
Actually, we should just pause there really quick. Turbulence is the ultimate example of multi-scale physics, right? That has really eluded us for a long time, right? It's a hard problem. And partly that's because you have the continuous cascade of space-time scales. But even if I had well-separated scales, that's still really challenging. I feel we have to first solve that problem. What if I have 2 or 3 distinct fast or slow scales, right, with 2 or 3 distinct spatial scales? How do we even do that one? If I can't do that, I can't do turbulence.
Yeah.
So, but if I can start understanding those problems, then I have a shot at figuring out like, oh, here's how scales connect. And what turbulence is going to be is now I'm going to have to connect it somehow in a continuous way, right? Anyway, yeah, I'm sorry.
Definitely.
That's exactly.
We can also jump.
That is the hardest problem.
Yeah, we can jump definitely inside the turbulence work you've been doing and talk about. The interesting thing you mentioned in that paper which is about Langevin, sorry, it's French, regression. There's this tension between, so there's this interesting thing that you can sample in a smart way so that the colored noise decorrelates and so it gets white, but also you can sample slowly enough that you can separate the deterministic component, I guess, the macro scale with the micro scale. So
Yeah.
what that means, the question is, what's the implication of that in terms of what's really happening, let's say? I mean, with this, we get a representation of what's happening, but can we say something about what's really happening? And then how do you see the relation between fat tails, so non-Gaussianity, super diffusion? How does this relate with multi-scale problems?
Yeah, I mean, so you're asking really hard questions, I think, because I think, when we look at these systems, like, for instance, you take something like a stochastic, you model something in a stochastic way, and you say, look, I've got some dynamical system, but I got this stochastic contribution to the dynamics, right? We tend to try to, so first of all, you can ask the following question. Is there really a stochastic fluctuation there, or is this my way of handling something I can't see? Mm-hmm. But by the way, in other words, if I had better measurement technologies, I would resolve that scale and say, like, so I often think about that stochastic piece as just being, I didn't measure it. There's some fast scale physics down there that I'm incapable of getting access to. And so I just see the statistics of it. And I'm going to try to bring that statistics up one level into my, so I kind of see it as a sort of almost a coarse graining procedure. Mm-hmm. Interestingly enough, if you go back to like quantum mechanics, this is a really interesting viewpoint of quantum, right? Which is quantum mechanics is a statistical theory. Now, the interesting thing about it, you're framing the whole Schrodinger equation as a statistical evolution of, the probability distribution. And really inherent in that is this idea of, I can't measure below a certain length and time scale. We're incapable of it currently, right? This is, and so I can only see a blurry vision of it, like a statistical version of this. Does that mean that it's really statistical down there? I mean, this is one of these things where, there's all this philosophy of quantum mechanics about Schrodinger's cat. But on the other hand, I see it just simply as, what? You don't have the measurement instruments capable of getting that really fast scale physics. So you just see its statistical version, and that's the best you can do. And I think what's interesting about sort of these stochastic modeling techniques is you're kind of now building a hybrid. There's a piece of it that's statistical that I can't measure, and then there's this part I can. And then you're trying to build the model the best possible, which is a hybrid between statistical fluctuations and some maybe deterministic dynamics. And so there's different ways to, so I always think of that as sort of like, that's our way of coarse graining things. But of course, it's always problematic when, of course, when we coarse grain these, we always assume Gaussian statistics, right? For the most part. But of course, that's mostly we assume these things because it's just a lot easier for us to do math on. Right? It's when you can characterize that entire process by two numbers, a mean and a variance, and then but even that's hard in stochastic calculus to get that right. So I actually am excited about this area because I feel like if we can start to think, so in my own personal view, to start thinking about, well, what if we can start setting up systems to start understanding this? What if I start thinking about this as a multi-scale problem? In fact, maybe what I'll do is make 3 time scales. So let's take that stochastic problem we had, which was said, here's this dynamical system, but it's got these stochastic fluctuations. What if I make a 3rd time scale, which is, so the stochastic fluctuations are an intermediate time scale. I'm going to make a much faster one. I'm just going to prescribe some deterministic dynamics way down here. And I'd really like to close the loop and say, can I understand how to coarse grain this up so I can make this rigorous mathematical connection down from these really fast microscales to what looks like a stochastic model? And then even when I start changing that really fast dynamical system, how does it produce fat tails? What's the kind of dynamical system that would produce fat tails for you, right? That when they coarse grain up, I got this fat tail distributions that I have to figure out. I have to work a lot harder to figure out how I'm gonna handle them, right? So I I don't know. That was a little bit rambling, but I feel like there's some really interesting potentials there when we start thinking about stochastic dynamics. University of Michigan is Karthik Durasamy, and he has this really nice way to build closure models, because this is the big thing with turbulence, which is, at some point you lose the ability to measure or resolve time space, right? Your measurement sensor has a limit. And so turbulence goes beyond that, right? So there's just a point at which you can't do it anymore. So the question is, how do you close that model off? And so there's some really nice emerging data-driven methods there. And I like that Karthik's work is really a nice piece of work. But also, I think that applies more generally. Like, if you start building these closure models, can we start understanding more about stochastic ODEs? Because if we start understanding how the closure relationship works, we could say, well, this thing that I'm getting that I'm calling a stochastic process is probably just an unresolved physics, which by learning these closure laws, I see how this works. Maybe it's going to give me more insight to do a better job on stochastic systems. That's my hope, right? Or maybe we can even figure out how to do a better job modeling, our stochastic systems, besides just saying, mean zero, mean and variance calculations on these stochastic processes.
Yeah.
So I'm hopeful we can do something there, but I think we have a long way to go on. But that to me is still getting right at that multi-scale physics problems of trying to figure out my quantities of interest are often macro scale quantities, but they're all being driven down here at the fastest space and time scales, and I need to figure out how they're connected. Otherwise, I get this uniscale physics model that just either is inaccurate or just simply puts in some stochastic fluctuation. And the only reason I do it is because I just don't know what's going on down there.
Interesting. Let me share that this made me think the following. So, this multi-scale does not really appear in celestial mechanics, but we have chaos, deterministic chaos.
Yeah.
And we have fractals. So we know there's fractals there. So there's some kind of multi-scale. I've always found weird that we have a deterministic system, but we cannot predict it. But from this physics point of view, if we say that in some sense, turbulence is like chaos. So at a certain point, there's something we cannot see, even if the model is deterministic. So we should treat it. We should stop trying to see everything, because there's a limit. But we still can do something about this separation. Once we do the separation, maybe we can solve. We couldn't do before. So I think this consideration applies.
This is such an interesting point you made, right? So even like you said, celestial mechanics, you can get chaotic behaviors, right? This initial sensitivity to the initial condition. Another way to think about this too is, in those same systems, you have also sensitivity probably to the parameters, right? So we normally, when we think about like Lorentz, right, we run it and say like, hey, look, if I change the initial conditions slightly, I just run it for a while, they look like, and then boom, they separate very rapidly. Same thing can happen if you just change the parameters a little bit. So same initial condition, but now parameterization. And this is what's interesting about the multi-scale physics. If we believe this kind of sensitivity is canonical, then micro scale physics, you say, why should I care? Don't I just see the average of this? Yeah, what if you see a slightly different variance? It's changing your parameterization maybe of the coarse grain, which then gives you a very different result, right? That sensitivity comes, and that's where I think the multi-scale aspect, even of these deterministic systems, it's that sensitivity in deterministic systems, which are kind of fascinating to look at, right? I think there's a lot there that we could do.
Yeah. And when you said something like, okay, we have the deterministic part, the stochastic, and then something else, where you're just, let's say, projecting imagination, or did you see something in which this is done already?
Oh, go ahead. Say that again. What was the question again?
When you said we can like have a model in which we separate like the stochastic fluctuation, the deterministic part, and then something else. Did you see somewhere along these lines already being done? Or is it just projecting, imagining things?
Yeah, no, so I think, okay, so so more broadly, I think from the modeling perspective is oftentimes we have a model that we kind of feel confident with, or we know comes from first principles models. We might have some what we call stochastic fluctuations, which are things that are beyond our measurement capability. The other piece that might come in though is just a discrepancy piece that where you say like, but maybe I'm just missing a deterministic piece to my model. Yeah. So what in general, I think of the model of having the part that we have discovered or we can derive, a part that maybe wasn't quite obvious to us that we could, maybe it's hard to derive or it's not obvious to us, but maybe is a missing piece of the physics. Usually it's small, right? Otherwise we would have worked hard to try to get it, right? And then there's the piece that's sort of the part that we just throw in as a stochastic or noise-driven term, which is that's actually beyond our ability to resolve because of our measurement capabilities. Right. So I definitely think that we have progress to make on building upon our let's say our Platonic model, our idealized model by bringing in discrepancy physics and then also bringing in the contributions of things that are beyond our measurement capability. And I think that that sets up a nice paradigm for us to think about how we might model things.
Nice. Yeah. And I keep thinking about the relations between fluid dynamics and aerospace engineering, dynamical systems in general. You worked a lot on PDEs, partial differential equations. And there was in particular one work with the use of deep learning. I cannot recall the title, but for goblet transformation that linearized PDE.
Yes.
So I think there's some potential of the use of the same techniques in the propagation of uncertainty in ODEs. So when you go from the deterministic ordinary differential equation to the Liouville equation or the Fokker-Planck equation in the stochastic case, have you ever? I mean, first of all, what you did in the PDE case, and then what's the difference with Galerkin methods?
Yeah. So that paper, maybe we could start there with deep learning for PDEs was, PDEs in general, right? Obviously, if they're nonlinear, they're typically, they can be pretty difficult to solve. And unless there's very few nonlinear PDEs that we can write down, general solutions for. That work was really inspired by, in some sense, this idea of Koopman theory, obviously. Which was this idea of some kind of transformation to make things linear. But that idea of Koopman theory shows up in other places, not where they didn't call it Koopman theory. And for instance, this comes to Burger's equation, right? So the Burger's equation is it's like a textbook PDE, right? In fact, this is the first, in my applied math background, you take a PDE course, one of the models you consider is something like Burger's equation, where you see like, look, here's this nonlinear wave breaking problem that you can, instead of getting shocks, you put a little diffusion there and you get these really interesting solutions. It's nonlinear, and you try to come up with techniques to try to characterize this. And so you see this very early on as a canonical example out of PDEs. The other thing you learn is that in the 1950s, Cole and Hoff independently learned, hey, look, you can make this transformation for this nonlinear PDE to make it linear. I mean, this is like magic, but it's one PDE only, right? And it would take quite a lot longer, another 20 plus years, till we get to the next set of PDEs that we could do this with. And this is the completely integrable PDEs. So nonlinear Schrodinger, Korteweg de Vries. There's a class of PDEs where we had this inverse scattering transform. And what it was a transformation for these completely integral PDEs that had an infinite number of conserved quantities, that you could apply this transformation and linearize the dynamics. So once you applied it, you're now in this spectral evolution space where all the dynamics is linear, and then you come back. And so it gave you another class of PDEs that I could solve explicitly by a linearizing transformation. So those are the PDE. So they're few and far between to come to, right? Like this is a small class. That was early 1970s, they actually laid out this architecture. Ablowitz, Kaup, Newell, Seeger, this AK and S inverse scattering theme kind of put it all together into a really beautiful mathematical framework. But it was quite a limited number of PDEs that could be solved with this technique. So, but inspired by that, the question was really from Craig Ginn's work on this was Craig and Bethany kind of really led that effort along with Steve and I, was to say, well, those are very specialized PDEs. Can you do this more broadly? And what they were able to find is that neural net could actually find linearizing transformations, even for something like the Kuramoto-Shibashinsky equation, which exhibits quite complex behavior, spatial temporal dynamics, in fact, chaotic spatial temporal dynamics. And the fact that they found a linear embedding was just kind of unbelievable. We knew that they could probably train a neural network and recover something like the Kohl-Hopf transform, or maybe even in a completely integrable case, come up with some representation of the inverse scattering transform, because we knew you could do it with those systems. But when they did it for the Kuramoto-Shibashinsky equation, it was like, wow, that's kind of unbelievable. And remarkably, like, if you would have told me, had me place a bet on whether they could have been done before they started that work, I'd say, probably not. That's too complex. We can probably do some of these other PDEs and automate some of this, but the fact they did it with that is still, to me, is just really remarkable. And actually, interesting enough, in going to conferences, when I show that slide with what they were able to do, a lot of people are kind of like, they actually were able to, that's amazing, because you would not expect that there is some coordinate system under which that KS equation has a linear operator that allows you to advance these solutions. That was just a remarkable thing. I also think it teaches us a lot about, okay, there's a lot for us to learn here on that system. Like somehow I feel like mostly what this has taught me is I'm pretty limited in my mathematical capabilities, right? Somehow I feel like if I knew more, or we need new math, because somehow this thing is figuring something out that is sort of remarkable. And somewhere down the line, I feel like maybe we could figure out a theoretical construct that says, yeah, of course this works. In fact, maybe I can linearize any PE, right? We just don't have that technology yet. But this is showing us that, well, it seems like it can be done. So maybe it should inspire us to build new methodologies to understand it. A little bit like, in the early days of chaos, right? Like, a lot of it came from first doing simulations, right? Like, I do this computation. This is really surprising to me to achieve this result, right? It wasn't like we had theory first and then we backed it up with computation. We first saw these computations and we were like, this seems impossible and wrong, right? And then we figured out, actually, no, not only were we right, but there's like a deep theoretical construct to it. And I actually think that kind of chaos embedding in a linear space is also kind of like, look at this, it can be done. That means we're kind of missing something. We need a lift in our mathematical technologies, because the computation is telling us something really important, just like it did. Now, it might be a little bit heavier of a lift, but just like we made progress in understanding nonlinear dynamics, chaos, and all this stuff, it took quite a little bit of time, right? People were so interested in this because it's so fascinating. My hope is that kind of work also helps us to be inspired to say, like, wow, there's a lot to learn here. And, this goes back all the way to the conversation we had at the beginning, which is, if we start automating things, or we're going to cut out things for people, like, I just feel all we're going to do is open even more interesting things for us to look at, right? That to me is the exciting part, which is every time we do this, we're starting to learn things like, wow, that actually worked. Now we have to have a bunch of people to do stuff to explain it. So we're actually creating more work. So
yeah, definitely. Yeah, this is a nerd joke, but it seems like, I mean, it's not even a joke, but it seems like the AI is the outcome of the training of the AI is the data we're getting to backpropagate it in the
Yeah.
consciousness, something like that. But yeah, definitely there's some work because I mean the surface of what we know is gonna get bigger and bigger, and in the meantime we need to keep educating people, I guess. So education maybe is part of this. And I have a question about this. I mean, you're a big inspiration, of course, with your codes online. I mean, when I started working after studying, I guess I think I emailed Professor Branton and played with Cindy like, I don't know, a week after I started, right away. And yeah, and then I talked with your papers a lot. Your videos resonated a lot. So why did you start it? Why did you start? Sorry.
Oh, start putting videos?
I don't know. I don't even know what it is. I would say the question is also related to how can you have such a nice collaboration. I mean, you can feel it. I don't know you and Professor Branton, but I know there's something there.
Yeah, no, Steve and I, you know, it's awesome. It's so fantastic to have a partner. And we have really similar passions about this. We're just, I mean, look, you know, life is a funny thing, right? We have all kind of our difficulties. Even being a faculty member has so many challenges, right? In the modern day, we're always needing to go out and try to get funding. There's so many distractions from doing the work that you really want to be doing all the time. But the commonality for Steve and I, and what has been such an amazing bond for us, is one is obviously the mutual respect we have, the love we have for each other as friends, but also just we love this. Like, you know, there's a lot of us that come into this field because, like, even what we were just talking about with this linear embedding of Kuramoto-Shevchinski and training. It is so overwhelmingly exciting to get a result like that. It's just like, you can do that. That is like amazing. So Craig, we were like, Craig is amazing. Like for us, Craig is just a superstar because he was able to do this thing that like, and it's so inspirational for us to think about, like, we have a lot more work to do. We have to understand this. And I know for us, it's just been so exciting to work with our students and our postdocs because they continue to bring a sense of wonder to us, because it's like, wow, what they are able to discover, how they're pushing things, how we're learning new things, because it's just so exciting. So everybody has their points at things that they get excited about. But ultimately, for Steve and I, it has been so much excitement around what we've been learning and how all these techniques have allowed us to learn more. And you know, frankly, at the end of the day, you know, machine learning is just another tool that has allowed us a viewpoint on these systems. You know, it's not like we're converts to machine learning just for machine learning's sake. It's just that what an amazing tool that is allowing us to see these systems that we love in brand new ways and learn so many new things about. So that's like the exciting part, and I think we're both into that. And the other thing that I think that drives us is the fact that for us, right? I mean, for all of us, like, learning science and learning things is such a slog. It's so much hard work that you have to put in, and we don't mind the hard work. But on the other hand, we've also felt so many times that after we've learned it, it's like, wow, this could have been so much simpler. If somebody would have just put a little code out and a little explanation. And sometimes, you know, there's a little pressure on us in math to make really fancy math, which kind of obfuscates what's really going on. And if you can explain things simply to people, first of all, I think they get more excited about it. But also, can you close that learning gap so we can do science faster? So for us, a lot of it, also where Steve and I are on the same page, is we want to get our students doing science faster. We want you to do science. We want everybody, like, and we also want to do science faster by getting that kind of information from others, right?
Yes.
So for us, you know, the more we can work with people and bring in a collaborative atmosphere and share, I think we can do even cooler things, you know, scientifically, mathematically. So that was really the ultimate inspiration. And then to see that it actually had a big impact on our students being able to get going faster with their research. And then it was like, oh, this is clearly a very good thing for us to be doing. Our students are happier about it. Our colleagues are happier about it, because they're not like, what did you really do? I don't have your code. And did you do this hyperparameter tuning you didn't tell me about? And that's the only way to make it work? Because we all know this happens, right? Like somebody wrote this code, they didn't put it out there, and there was some magic hyperparameter tuning they did that you're never going to be able to do it. No. And it's super frustrating, right? Because now you're frustrated because you feel like you wasted a lot of time, versus if people are transparent and can show you and actually put the code out there, put the data out there. I just think that it's so much healthier overall. Mm-hmm. So it's been fun, and we kind of thrive, and we have a very common viewpoint, and also, like I said, just our students and postdocs are so awesome that, I mean, they're really the stars of the show. We get to be sort of front people for them, but at the end of the day, they are just so talented, and you know, they're actually doing all the cool work. So
yeah, I guess we can close it here. It was a final remark, a beautiful final remark. So thanks a lot for the conversation.
You bet. Thank you so much for having me, and a real pleasure. Hopefully this is helpful for people. So.